Hello guys, so today we are going to talk about gas laws. So in talking about gas laws, we are going to relate more than just pressure with temperature, volume, and number of moles like we did in section 11.1. So we are going to be looking further into these relationships and further classifying them so that we can get a better idea of gases and how they're going to behave. So the first of these gas laws that we're going to talk about is Boyle's law, and Boyle's law is relating pressure and volume. Now, as we should recall, pressure and volume are inversely or indirectly related, which means as one increases, the other decreases. So as pressure increases, volume decreases, and this is of course assumed that temperature is constant. And in addition to temperature being constant, this also assumes that N, which represents our number of moles, is constant as well. Okay, so this is only looking at how pressure and volume are related as long as we're keeping these other variables the same. So in order to be able to answer this question, our temperature can't change, nor can the amount of gas that we have. But pressure can change, and we can look at how volume will change, or volume can change, and we can analyze how pressure is going to change. So we have that under a constant temperature, the volume of the gas varies inversely with pressure. And what that means is we are going to use this equation, P1 V1 equals P2 V2. So it doesn't matter in this equation which you assign as your variable number 1, but you have to have the corresponding volume with it. And we will talk about what that means a little bit further. So let's do this practice problem. So using Boyle's law, which remember is P1 V1 equals P2 V2, we are going to say a balloon consists of 30 liters of helium gas at 103 kilopascals. What is the volume of the helium when the balloon rises to an altitude where the pressure is only 25 kilopascals? So nowhere in this question do we mention temperature, which is a good indicator that temperature is going to remain constant. So usually if they leave it out, if they don't include it, it is something that isn't changing and it's going to stay constant. So we're going to list out our knowns. So we know two pressures and we know the starting volume. So what I mean here is these two guys are linked together because they are our initial conditions. So 103 kilopascals exists under that conditions of 30 liters. It doesn't matter if I technically label that P2 and V2 as long as they are kind of linked together in being in that second set. So it doesn't matter if you want to assign them P2, V2, or if you want to do P1, V1, as long as those two stay together. And what we're looking for is the volume after our pressure changes. So we're looking for V2 in this scenario after we change our pressure. So you'll use Boyle's law, again, P1, V1 equals P2, V2, and we can calculate that unknown V2. So what we've done here is there's a rearrangement of V2. So a rearrangement of P1 V1 equals P2 V2. In order to get V2 by yourself, you have to divide by P2. So divide by P2, divide by P2, and that's how we get this equation here. That is not necessary to do before solving the problems, but it can make it a little bit easier. Now all we have to do is sum into those variables that we defined as our knowns and solve for volume. And another thing that I want to note is in P1 V1 equals P2 V2, there are no set pressures or volumes that need to be included in that. So this pressure can be in ATM, it can be in torr, it can be in millimeters of mercury, but whatever this pressure is, this pressure also needs to be measured in the same thing. Same goes for volume. Whatever that volume is, that volume needs to be the same. So your pressure units need to match and your volume units need to match, but that is the only requirements for solving these types of problems. So next, what we will do is you should always sort of evaluate your response and see if it makes sense. So does this result make sense? So we already talked about what we know is going to happen from our relationship. So we know that pressure is decreasing, so that means we have to have an increase in volume. We saw that our volume does increase, so that leads us to believe that our answer is correct. Obviously, this evaluation will not help correct any sort of accidental calculator errors that may occur. All right, so our second gas law that we're going to talk about is Charles's law, and Charles's law relates temperature and volume. So we are going to talk about, okay, as temperature increases, how is volume going to increase? Or maybe not increase or decrease. How is volume going to change? So under these conditions, we assume pressure is constant. So whatever isn't included in the law is going to be held constant. So in this scenario, pressure is constant as well as the number of moles. So as temperature increases, the volume increases. So temperature and volume are directly related, and that should make sense. Temperature leads to an increase in kinetic energy, which then means our particles are going to be moving faster. The particles moving faster means they have more energy to spread out, which means we're going to have an increase in that volume. All right, now this is not to be confused as to before when we talked about temperature and pressure. We said that pressure would increase as temperature increases, but that can also be confusing because pressure and volume are indirectly related. So how can both pressure and volume increase as temperature increases? Well, before, when we talked about pressure and temperature, we talked about it under the condition that volume is held constant. In this scenario, we're talking about temperature and volume in which pressure is held constant. So the variables that are being held constant affect the equation and your conceptual processing of the question a lot more than you may realize. So it's something that you definitely want to keep track of, is under which law, what are we going to have constant? And remember, it's just whatever is not involved in that expression. So Charles's law states that the volume is directly proportional to its Kelvin temperature. So this is the one thing that you must have a unit for. Temperature must be in Kelvin. And if you recall, to get temperature into Kelvin, you take the degrees Celsius temperature plus 273 K, gives us our temperature in Kelvin. So we have V1 over T1 equals V2 over T2. Now, some people prefer the linear way of looking at it, so you can cross multiply and get V1 T2 equals V2 T1. That is optional. You do not have to do it that way, but that is another way that you may write it out and that you may find easy to use. So Charles's law is a quantitative relationship between volume and temperature, and that he found that if a volume changes by 1/273rd of its original volume for each Celsius degree at a constant pressure and at an initial temperature of 0 degrees Celsius. So basically, he found that you have to use Kelvin in order for this relationship to work. So temperature of -273 is referred to as absolute zero. So this is absolute zero is at 0 Kelvin. Important to note, this is theoretical, not a value that we have actually been able to get to. And the relationship between the two, Kelvin equals 273 plus degrees Celsius, which we already talked about. You must always convert to kelvins in order to be used in these equations. So let's do this practice problem. A balloon is inflated in a room at 24 degrees Celsius and has a volume of 4 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What is the new volume if the pressure remains constant? So the first thing that we want to do is assign all of our knowns and our unknowns and our variables. Like before, these two need to stay lumped together because they are under the same conditions, but again, it doesn't matter if I assign that V2 and T2. And we know right now these are incomplete. Our temperatures cannot remain in Celsius. We need to convert them to Kelvin. So first step is to convert your temperatures to Kelvin. Then we can rearrange Charles's law to isolate V2. Remember, it's V1 over T1 equals V2 over T2. If we want to isolate T2, we will multiply, and that's how we get V2 by itself, as in this equation. So then we just have to substitute our values in using kelvins, and if you see here, kelvins will end up canceling out and you'll be left in liters. Now, that volume doesn't have to be in liters, it could be in milliliters, it could be in centimeters cubed, but whatever this volume is what the volume of your unknown would also be. So we can see here, as our temperature 2 increases, so does our volume, and that is the relationship that we expect to see. So that evaluation makes sense and offers kind of a valid check for our thought process. The third law that we are going to talk about is Gay-Lussac's law, which relates pressure and temperature. So we should know that pressure and temperature are directly related, and this is under the conditions that volume is held constant. And it was named after Joseph Gay-Lussac, who discovered it. So if you have noticed, the laws that are indirect are like P1 V1 equals P2 V2. They're on the same side. We have no fractions, it's just multiplication. And this is indirect relationships. Direct relationships always has them stacked on top of each other in a fraction. So that's another way that can help you remember what's going to happen. So in this one, just as in the last one where we talked about volume and temperature, we had V1 over T1 equals V2 over T2. Any direct relationship is going to have fractional relationships. So that's just one way that you can help keep them straight. So the Gay-Lussac's law is P1 over T1 equals P2 over T2. Again, temperature here must be in Kelvin. Pressure can be in any sort of unit, but whatever one of your pressure is, the other one has to match. So let's do this practice problem. Aerosol cans carry warnings on their labels to say not to incinerate, so burn them, or store the cans above certain temperatures. This problem will show why it's dangerous to dispose of aerosol cans in a fire. So the gas used in an aerosol can at a pressure of 103 kilopascals at 25 degrees Celsius. If the can is thrown into a fire, what will the pressure be when the temperature reaches 928 degrees Celsius? So the first thing that we want to do is we want to write out all of our knowns. So we write out all of our knowns. Again, doesn't matter if you labeled that one P2, T2, as long as they are together because they are under the same conditions. And then we need to use Gay-Lussac's law to calculate our unknown. And we also need to convert temperature to Kelvin as we have done here. So remember P1 T1 equals P2 over T2. So what we want to do is we want to isolate P2, so we will multiply by T2. And in doing so, we get P1 times T2 over T1 equals P2. So again, you don't have to rearrange, but it can be easy because now all we have to do is substitute into our equation. Kelvins cancel, and our P1 unit, which is kilopascals, is what our P2 is going to be solved for in. So we get 415 kilopascals, which should make sense because as temperature increases, we also see that we are going to get a large increase in our pressure, and this large increase will cause a burst in the can, which is why it's dangerous. So it should make sense because we see that relationship as one increases, so does the other. So our last gas law that we're going to talk about is the combined gas law, and as it implies, it is going to combine all of these varying factors. So we are going to be able to look at situations in which pressure, temperature, and volume all are going to vary at the same time. Now, the one thing that is held constant here is the number of moles, and we need to remember that because we will have a law later on that then includes what happens when the number of moles changes. But right now, we are just looking at what's going to happen when pressure, volume, and temperature change. So our combined gas law should look very familiar. We have that relationship V1, T1, but also P1 times V1 and P1 over T1. So basically, we have Charles's law right there, P1 times V1. We have, not Charles's law, Boyle's law, right there, P1, V1. Charles's law, V1, T1, and then Gay-Lussac's law, all combined together. So we have P1 times V1 over T1 equals P2 times V2 over T2. And again, the only restraint here is temperature must be in Kelvin. So let's look at a scenario in which we are going to use our combined gas law. So we want to know the volume of a gas-filled balloon is 30 liters at 313 Kelvin and 153 kilopascals. What would the volume be at standard temperature and pressure? So we need to recall that STP is what happens when pressure is equal to 1 atm and temperature is equal to 0 degrees Celsius. So they don't exactly explicitly say what we're changing them to, but we do have that implied. So we need to list out our knowns and our unknowns. P2 here, that 103 is equal to 1 atm. So there was a little bit of a conversion there that we did not get to see. Same here, T2 is equal to 0 degrees Celsius, but all we know is we have to add 273 to that. So all we're looking for is V2, so we will sub that into our equation. Again, this has been rearranged. We do not have to go about rearranging it, but you most certainly can if you would prefer. So you substitute your known quantities in. Our volume one is in liters, which means our volume coming out is in liters as well. So decrease in temperature and decrease in pressure have opposite effects on the volume of the gas. So in order to evaluate which one is going to, or how it's going to change, that's why we need to use this combined gas law. Because just looking at it and being able to logically think about it, now we have these sort of differing effects that are going to alter what happens. So to summarize, Boyle's law is P1 V1 equals P2 V2. Charles's law is V1 T1 equals V2 over T2. Gay-Lussac's law is P1 over T1 equals P2 over T2. Avogadro's law is on there. I'm going to put a star by that. We won't use it explicitly, but it does come into play when we are going to talk about our ideal gas law. So just keep that one in the back of your mind. So we have our section quiz. I encourage you to pause the video and attempt these on your own. So if the volume of a gas in a container were reduced to 1/5 the original volume at a constant temperature, the pressure of the gas would be 5 times the original pressure. So what I do is I would plug this into an equation. So we have volume and pressure, so we have P1 V1 equals P2 V2. So the volume of the gas in a container was reduced to 1/5. So let's say this is 5, and then V2 goes to 1 because it's reduced by 1/5. And this pressure was 1. It could be 2. It could be anything. I'm just saying it's going to be 1. We want to know how P2 is going to change. Well, 1 times 5 is 5. 5 equals P2 times 1. So P2 equals 5. So you can see that there is 5 times as much. Question 2. A balloon appears slightly smaller when it is moved from the mountains to the seashore at a constant temperature. The best gas law to explain this observation would be Boyle's law. That's because we are relating pressure and volume. So the only thing that's changing here, we have the difference in the altitude, which is a change in pressure, and we want to determine how that is affecting that change in volume that we are observing. At 46 degrees Celsius and 98 kilopascals pressure, a gas occupies a volume of 0.6 liter. How many liters will it occupy at 0 degrees Celsius and 20.8 kilopascals? 2.20 liters.